We've come to our last set of notes for Unit 5. Today we're going to be talking about the Fundamental Theorem of Calculus Part 2, 2.0. And we're going to get a couple other, another formula for you. All right? So, another important formula. Another big day for us. Okay. Let me introduce this to you. First of all, I would like to consider this integral. Let's say that we have the integral 4t cubed plus 2t minus 3 dt. So we have that integral. Right now it's an indefinite integral because it has no boundaries. Okay, we know that we could find a function using the power rule whose derivative is this, right? So we know that. We've done that already. I'm going to put some boundaries on here. I'm going to go from 2 to x. Okay? Yeah, we could have a variable up here. That's not a problem. I'd like to go ahead and find this definite integral. Okay? Do you agree that my answer is going to have an x in it? Because we're going to find the antiderivative and then we'll be putting x in place of the t's. So my answer here will have an x in it. Let's go ahead and do that. I think I'm going to do it over here. So I'm going to have power rule times. So t to the fourth. Raise your power by 1, divide by your new power. It's going to be a 1. Raise your power by 1, divide by your new power. It's going to be another 1. Minus 3t. And now we're going from 2 to x. So I'll have x to the fourth plus x squared minus 3x minus 2 to the fourth, 16, minus 2 squared minus 3 times 2. So this will be x to the fourth plus x squared minus 3x. Let's see, we have 16 minus 10 is 6, so we'll have minus 6. Okay? So this definite integral yielded this, right? Now I'd like to come in to my answer here, and I want to take the derivative of that with respect to x. What's the derivative of that with respect to x? Well, the derivative of x to the fourth is 4x cubed. The derivative of x squared is 2x. The derivative of negative 3x is negative 3, and the derivative of negative 6 is just 0. So the derivative with respect to x of my answer gave me this. How does that relate to my integrand? Is there a relation there? Well, there sure is a relation there. It's this same thing, except instead of t's, I have an x there. Is that going to always work? And another question, what happens if this was some other number, like a 3, or a 5, or a negative 10, or something else, any other number? Would this have still stayed the same? Yes, it would have. This would have been different, so that would have been different. But when we take the derivative of a constant, we're going to get 0. So the derivative would always be back to this, no matter what that is. Okay? So if we follow that pattern, what if we had the integral of sine of 7t plus 8t cubed plus 1 dt, and let's take this from 5 to x, okay? But I'm going to go ahead and take the derivative of that all together. So we're taking the derivative of this integral, okay? The derivative of that definite integral. just like we did here. We found the definite integral, then we took the derivative of it. So let's apply what we just learned. This is going to be the exact same thing I have written here, except instead of t, I'll have an x. Sine of 7x plus 8x cubed plus 1. That's it. That's it. What happened to the 5? Well, when we took the derivative of that number, we got 0. That's what happened to that 5. So the 5 will not come into play here, because the derivative of 5 is 0. Okay? All right. Now let's consider this one. The derivative of, let's go from 4 to 3x squared, not just an x. And let's just make this 5t plus 1. Okay? All right. Well, this is not just an x this time, right? This is not just an x. It's a 3x squared. So we're going to have a little chain rule going on here, okay? Little chain rule, because it's not just an x. So I am going to replace t with 3x squared. I'm going to replace t with 3x squared. But I'm going to apply a little chain rule and multiply by the derivative of 3x squared, 6x. That's why I left a little blank out in front. Okay? That's going to be my answer. I could distribute that and make it look a little prettier, but that's it. Okay? So, when this is not just a plain x, remember you need a little chain rule. So this is the derivative of 3x squared. Okay, do another one. What if we have x to sine x of e to the t squared dt. And we're taking the derivative. This is only valid if you're taking the derivative of an integral. Derivative of an integral. Derivative of an integral. Okay? The derivative of an integral gives you some form of that function. Okay? So, this is going to be, I'm going to begin at my top boundary, replace t with sine x. I'm leaving a space because I know I'm going to have a chain rule here. E to the sine squared x times the derivative of sine x. The derivative of sine x is cosine x. This is not just a number this time. That means it's going to come into play. Minus, I'm going to replace t with x. The derivative of x is just 1. So that's going to be my answer. So always remember, this is only true if you're taking the derivative of an integral. That's the only time you can do this. This is the second fundamental theorem, or fundamental theorem of calculus 2.0. Okay? Let's, I'll save that. I'll do a couple more examples in a moment. Okay. So let me write this. Second fundamental theorem, or fundamental theorem of calculus 2.0. Okay, and that says if you're taking the derivative of an integral, from, and it's going to have boundaries. Okay, it's going to have boundaries. I'm going to make these boundaries each have the possibility of being a function of x. So I'm going to go from h of x to g of x. So you can have x's here. The inside function will be some other letter like t. Okay? Start with your top boundary, take the derivative. And then put your top boundary in for t. Minus, now go to your bottom boundary and do the same thing. G prime of x, take the derivative, times, now replace your function t with that h of x. This is the fundamental theorem of calculus 2.0. Alrighty, let's do a couple of examples before we go and get this other formula. I'm going to go to your example sheet, and let's do the first 4 examples. So, the first thing I see here is I'm taking the derivative of an integral. Derivative of an integral, I think that's that second fundamental theorem. Derivative of an integral. I look at my top boundary, it's just an x. My boundary is a 3. So I'm going to be replacing t with x. The derivative of x is just a 1. So if you want to use chain rule, you can, but that derivative is just going to be a 1. Square root 1 plus x squared. Period. You're done. Because the derivative of 3 is 0. Okay, number 2. Derivative of an integral. Derivative of an integral is when we can do this. Start at the top, boundary, take the derivative. Derivative of natural log x is 1 over x. And now replace t with natural log x. The bottom boundary is a 4, the derivative of 4 is 0, so this last piece will just be 0. So that's our answer. Okay, derivative of an integral. Start with your top boundary. Take the derivative. 3x squared. Replace t with x cubed. The bottom boundary is x. The derivative of x is 1. So I'll just have a 1, and then I'm going to replace t with x. And that's it. Okay, number 4. Derivative of an integral. Second fundamental theorem. Start at your top boundary. It's a -2. The derivative of -2 is 0. 0. Minus, now go to your bottom boundary. The derivative of your bottom boundary is a negative sine x. So that will make this a plus sine x times, and now we're going to replace t with cosine x. That's it. Number 5. They give me that g of x is this integral. What is g prime of x? Well, g prime of x would be the derivative of that integral. Right? Derivative of an integral. From 1 to x, we're just going to replace t with x. And we're done. We see that one quite often in FRQs. Okay? All right, let's go back to my little intro here. Okay. Now, Way back in Unit 1, we talked about the average rate of change. Of f from A to B. And we said that that was change in f divided by change in x, which was f of b minus f of a divided by b minus a. Change in f over change in x. That was our old Algebra 1 slope. We also called this AROC, right? Average rate of change, AROC. Old slope, Algebra 1 slope. Okay? Well, now we know, using the first fundamental theorem, fundamental theorem 1.0, f of b minus f of a is equal to the integral from a to b of f prime. Right? So, this average rate of change, AROC, is 1 over b minus a times the integral a to b of f prime. Must be true. Must be true. Now, this is AROC, average rate of change. The rate of change of f, is f prime, correct? So this says that the average f prime is this. The average f prime is this formula with f prime in it. So what would the average of g prime be from a to b? The average of g prime would be this, right? The average of h prime would have an h prime over here. What about the average of something else? What about the average of g double prime? What would that be? Well, that would just have a g double prime over here. Do we need any primes at all? What would be the average of g from a to b? Well, that would be this with a g here. So whatever you're finding the average of, that's going to be what's inside this integral. So the average of f from a to b is 1 over b minus a integral a to b of f of x dx. Average of any function. Think about what we just showed here. If you have some function from a to b, we now have a way to find the average value of that function. That's pretty significant. The average y, the average height of that function. We now have a way to do it. This is a big formula. AP loves this formula. Big, big formula. You have to know that formula. Okay? Have to know it. Here's how I remember it. If I ask you to find your average test score, if I ask you to average your tests, what's the first thing you're going to do? You're going to add up your test scores, right? You're going to add up your test scores. Right? And then you're going to divide by however many test scores you have. Correct? That's what you're going to divide by. How do we add in calculus? In calculus, to add, we use a summation. We use our integral. That's how we add things. So if you want the average of f, the first thing you're going to do is add up your f's. And then you're going to divide by something, b minus a. Don't forget to divide by that b minus a. Okay? So, if you're asked to average f, f is in your integral. Okay? Average of f is the integral of f divided by b minus a. I say that repeatedly because for some reason kids like to, I know why, when I ask them to find the average of a function, they want to put like the derivative of that function over here because they're getting confused with the fundamental theorem of calculus. But if you're averaging a function, your function is in the integral. Let's look at some examples. Number 6. Find the average value of g on the integral from 1 to 4. All right. The average value of g will be 1 divided by b minus a, integral 1 to 4 of g, not g prime, g. So this is 3x squared minus 2x. So this is 1/3. Let's do the antiderivative. Raise your power by 1, divide by your new power, that will just be a 1. Raise your power by 1, divide by your new power, that will just be a 1 again. So this is 1/3. 4 cubed is 64, minus 4 squared is 16. That's what we get when we put 4 in for x, and now we're subtracting what we get when we put 1 in for x, 1 minus 1. So this is 1/3 of 64 minus 16 is, goodness, 8/48. So that is 16. How about that? All right. So the average value of g on that interval is 16. If we were to graph this, and we would see that that probably makes sense. Average value is 16. Okay. At what values of x does this function equal the average value of f on this interval? So first let's find the average value of f on that interval. So the average value would be 1 divided by 3 minus 0, integral 0 to 3 of f, not f prime, f. So this gives us 1/3, okay, antiderivative, 9x minus, raise your power by 1, divide by your new power. We're going from 0 to 3. Put 3 in for x. Put 3 in for x. 3 cubed divided by 3 is just 3 squared. 27 minus 9 is 18, and 1/3 of 18 is 6. So the average value of f is 6 on that interval. Now we want to find the value of x, or the values of x, that this function is equal to that. So now we want to take our function, set it equal to 6, and solve for x. We're going to get x squared is 3, so x is plus and minus square root of 3. We get to use a calculator this time. We want at what value of x does h equal its average value on the interval from 1 to 2. So the average value of h on that boundary, on that interval, is 1 over 2 minus 1, which is just, well, 1, integral 1 to 2 of h. Okay, and we get to use our calculator, so I think I will. I'm going to grab my calculator. This is all just 1 out in front, so I'm going to go math 9, 1 to 2, 1 divided by x cubed. 0.375. Exactly. I like that. All right. Now we're going to set h equal to 0.375, right? So x cubed will be 1 over 0.375, and x will be the cube root of 1 over 0.375, which would be a safe stop spot, by the way. But in a multiple choice question, which it probably would be, I would do 1 divided by 0.375 all to the 1/3, which is cube root. So 1.387. Okay. Number 9, find the value of k such that the average value of f is equal to sine x on the interval 0 to k is 2 over pi. Okay, they're talking about an average value of f on this interval, and they tell me what the average value is. So I'm going to set up the average value equation. The average value of f is going to be 1 over b minus a is k minus 0, or just k, integral 0 to k of f, which is sine x dx. And they tell me that that is equal to 2 over pi. And we want to find k. All right? I cannot use my calculator on this because of that k right there. Can't do it. I have to do this antiderivative by hand. So I have 1 over k times the antiderivative of sine x is a negative cosine x. And we're going to take that from 0 to k, and I know that that's equal to 2 over pi. I could at this point multiply both sides by k. I think I will multiply both sides by k. So I'm going to have 2k over pi on that side. All right? Over here I'll have negative cosine of k minus negative cosine of 0, which is a negative 1, right? So this will be a negative 1, so that will make this a plus 1. Now I want to find k from that. I think I'm just going to move everything to the right-hand side and use my calculator. Okay, I'm going to go to my graph, put all of this in place of k. I'm using an x because it's easier to reach. And then I'm going to put 0 over here. And I know I only want from 0 to k, so I don't want any negative values, right? Oh. So I'm just going to graph this and see what it gives me. It looks like 0 is 1, and then I have these other 2 values that are possible. I don't want to use 0 because that's one of my boundaries, right? So I'm going to get these other 2 values here. So second calc 5, enter, enter, enter. And I get 1.5707. Does that look familiar to you? Oops. 1.5707 dot dot dot. Does that look familiar to you? That's pi over 2. If you recognize it, great. If you don't, that's fine. Just round it, make it 1.571. But that is pi over 2. And then the next value, second calc 5, go over here a little bit closer, enter, 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 is pi. And I'm sure you recognize that, 3.14159. Okay? Or you can just round it to 3 decimal places, or yeah, make it 3.142. That's fine also. So that's how I would do that problem. Okay, let's take a look at number 10 here. How are we doing on time? Yeah, we're doing good. All right. The graph of function f defined, this is a no calculator question, defined from -1 to 5 consists of a quarter circle and 3 line segments. So this is the graph of f. And g is given by this integral. Well, if they give me that g is this integral, I know this type of question. I know that they're going to be asking me questions about g all throughout the problem. Even though they gave me the graph of f, they're going to be asking me questions about g. And sure enough, in part A, find g at all of these values. Well, let's start with the first value, g of 0. G of 0, we're putting 0 in for x, correct? So that would be integral 0 to 0 of f of t, which is just 0 because our boundaries are the same. Easy. Next up, we'll find g of -1. Well, for g of -1, I'm going to replace x with -1. Since my boundaries are off, my lower boundary is higher than my upper boundary, the first thing I need to do is switch those. Make it a negative and then -1 to 0. So we'll have negative, and now the integral from -1 to 0 of f, I can go and use my areas, right? Area from -1 to 0. That's this area here. It's above the x-axis, so the integral is positive. So we're going to have 1/2 base times height. That would be my safe stop spot, but I will likely have to use it again. That would just be a -1. G of 2. Replace x with 2. We'll have the integral 0 to 2 of f of t. Okay, well the integral 0 to 2 is just the area from 0 to 2. The signed area, it's going to be positive since it's above the x-axis. So the integral gives you the signed area. So we'll have 1/4 pi times r squared, r here is 2. That would be safe stop, but this is pi. This would be a safe stop spot. And lastly, we're asked to find g of 5. So that would be the integral 0 to 5, replace x with 5. 0 to 5, I'm going to have this positive area. So we just found that was pi, right? And then we're subtracting out this other area. So this area, I think I'm just going to count squares. I have these 2 full squares. This is going to add up to 1, and this is going to add up to 1. So this is going to be 4. I like it when they give me the grid in the background so that I can just count squares. Part B. Find all values of x in the open interval -1 to 5 at which g has a relative maximum. And we need to justify. So g has a relative max when g prime goes positive to negative, right? So we need g prime. Do we know anything about g prime yet? We know g, we know f, we don't know G prime yet. So we have to say what G prime is. G, we know, is the integral 0 to x of f of t dt. So what is G prime? Well, G prime is the derivative of this integral. Which is just f of x. So G prime is f of x. So this graph of f is also the graph of G prime, just like we did in the notes a day or so ago. Okay? So, if I need to know where G prime goes positive to negative, I only have to look at this graph, because this is the graph of G prime. And this graph goes positive to negative at x is equal to 2. And that's the only place that G prime goes positive to negative. So I will say G has a relative max at x is equal to 2, since G prime goes from positive to negative there. You must, in this, you must tell me what G prime is equal to. You have to. Okay? You actually don't need to write this step, this part. And you don't need to write this because it was written above. But you have to tell me that G prime is f of x here if you're going to use this reasoning. Okay? All right, part C. Find the absolute minimum value of G on this closed interval and the value of x at which it occurs. Okay? Absolute, we're going to use closed interval test. Always. Our independent variable is x. We're finding the minimum of G. If you prefer to write G of x, you can. Start with your boundaries. These are our bounds. I like to say what I'm doing. Those are my bounds. I also need to know where G prime is 0 or undefined. G prime is 0 or undefined, right? So where is G prime 0? G prime is 0 at our boundary and at x is equal to 2. So at x is equal to 2 only. Okay? You need to write that to show why you're using that 2. All right? It's kind of clear why you're using these boundaries, but you need to say why you're using 2. All right? G at -1 is that one that we found previously. G of -1, we did find that. That was -1. G of 5, we found up here in part A, is pi minus 4. G of 2, we also found that was pi. Okay? Which is the lowest? Which is the lowest? Is -1 lower than pi minus 4? Pi is 3.14159, 3, a little over 3. If we subtract 4 from something a little over 3, you're going to be higher than a -1, right? So G has an absolute minimum value of -1 at x is equal to -1 by closed interval test, which is clear because there's our closed interval test. Okay? So again, we're using these G values found previously in the problem. If we had not found those values, we would have had to go and find those. Okay? Part D, find the x-coordinate of each point of inflection of G. Point of inflection of G. Remember, that's where G prime, double prime changes signs. Justify your answer. So we need for G double prime to change signs. Up until now in this problem, we have not stated what G double prime is, so I'm going to say it now. G double prime is the slope of G prime, which means that G double prime is the slope of our graph that we're given, F. Okay? We've already said that G prime is equal to F, so all we really have to do here is say this. But you do need to say it. You need to say what you're going to be looking at. We're looking at where does the slope of G prime change signs. Where does the slope of G prime change signs? Well, the slope changes signs at x is equal to 0. Does the slope change signs here? No, it goes from negative to negative. The slope does change signs here. It goes from negative to positive. So at x is equal to 3. 0 and 3. So G has a point of inflection at x is equal to 0 and x is equal to 3, since G double prime changes signs there. That's it. Fun stuff. I love this stuff. There's almost always a problem like this on the AP exam. Almost always a problem like that. Some form. And they can ask a variety of things, but it's almost always there.